Brownian motion, a random process used for modelling particles moving erratically in a fluid, stock prices, any system subject to random noise. And then there's the zeta function studied by Euler in the 1700s, extended to the complex plane by Riemann. It's got deep connections to number theory, prime numbers, and subject to a famous unsolved conjecture. So two very different things. But why does zeta keep appearing in the study of Brownian motion? And in so many different ways? I don't know, no one does, but that's what I'll look at today. Now, when Riemann extended the zeta function to the entire complex plane, he didn't just extend it, he also completed it. First, by multiplying by the gamma function of s over 2, and by pi to the power of minus s over 2. Now, this factor is fairly easily understood, and it makes the whole expression symmetric in reflecting about a half, replacing s by 1 minus s. Then he multiplied by s times s minus 1, which cancels out the poles at 0 and 1. Then he multiplied by a half to... well, that bit is actually a bit annoying. Anyway, this is an entire function on the complex plane. It's got no poles, and it's called the completed zeta function, or Riemann Zeta function. And it's still symmetric under reflecting about a half, which is the celebrated functional equation. But did you know that this is the moment function of a probability distribution? Well, it would be if it wasn't for this annoying factor of a half. So let's move that across. Did you know that 2 times psi is the moment function of a probability distribution? That is the generalized moments of a positive random variable x for all complex exponents s. It's the same thing as the moment generating function of log of x, so it uniquely determines the distribution. And this generalized moment function is also called the Mellin transform of the distribution. But what is this mysterious probability distribution? And is it actually useful for stuff? Let's have a look. Well, let me consider something completely different. Suppose we're sampling independent values from some distribution. Maybe we're measuring the heights of people. After a lot of these measurements, we can then try and estimate the distribution of heights amongst the general population. To do that, we could just use the observed distribution of heights actually measured, which is called the empirical probability distribution. Under this, the probability that x is less than any fixed value is just the proportion of the observed heights that were less than this value. But maybe you already have a proposed or theoretical distribution for the heights of people. It could be normal or log normal, whatever, any continuous probability distribution. And this is called the null hypothesis. The question is our observed distribution from the data actually consistent with this? Well, we need some statistical test, right? And we could just look at the difference between this empirical distribution function and the theoretical one. If this is big, then we would want to reject the null hypothesis. So let's take the maximum of this distance over all values of x. And in fact, this has a name. It's called the Kolmogorov-Smirnov statistic. And the idea is if the two was too large, then we would reject the null hypothesis. Say for a 99% confidence level, then you would choose a value which is less than this with probability of 99% under the null hypothesis. But what is the distribution of this statistic? Well, as the difference of the empirical and theoretical distributions is an average of n independent samples, its standard deviation will be inversely proportional to the square root of n. And in fact, the central limit theorem tells us that multiplying it by the square root of n, this converges to a normal distribution. And the square root of n multiplied by this statistic also converges in distribution, and its limit has a name. It's called the Kolmogorov distribution. But what is that? Well, it's possible to compute the probability density as an infinite sum, but its moments do have a closed form. The expected value of d to the s, here s does not have to be an integer, this works for any complex value. So these are generalized moments and uniquely determine the distribution. Anyway, this equals s multiplied by 2 to the minus s over 2 multiplied by 1 minus 2 to the 1 minus s multiplied by gamma of s over 2 multiplied by zeta of s. So we've got the zeta function again. But maybe you don't want to use the Kolmogorov-Smirnov statistic. Maybe the empirical distribution function lies above the theoretical one and rarely drops below it. Maybe we want a statistic which takes this kind of behavior into account. Well, you could just take the maximum positive difference and separately take the maximum negative difference between the distributions across all values of x and then add these together. And in fact, this is known as the Kuiper statistic, and it has some advantages over the Kolmogorov one, like being more sensitive to differences in the tails of the distribution. And multiplying by the square root of n, it converges to a limit distribution again. Its density is known as an infinite sum, but it's got no name. As far as I could tell, this distribution doesn't have a name. So I'll take the liberty of naming it here. I'll call it the Kuiper distribution. And we can compute the generalized moments of this just like we did with Kolmogorov. And if we do that, we get the expected value of v to the power of s is 2 to the power of minus s over 2 multiplied by s times s minus 1 multiplied by gamma of s over 2 multiplied by, yes, you guessed it, zeta of s. So zeta again. But even better, this is almost the same as the Riemann psi function or completed zeta function. And rearranging, this is exactly the same as half of pi to the power of s over 2 multiplied by 2 psi of s. So actually it makes sense to scale our statistic by the square root of 2 over pi, and this has generalized moment 2 psi. And looking back at Kolmogorov's distribution, we could also scale that by the square root of 2 over pi, and it has generalized moment 1 minus 2 to the 1 minus s over s minus 1 times 2 psi. But why? Where is the zeta or psi function coming from? What's it even doing here? Well, let's have a look at Brownian motion. So let's go back to Brownian motion. It's a continuous stochastic process with independent increments, and at any time t, it's normally distributed with mean 0 and variance t. Then, if you fix a time t and you condition on the Brownian motion being 0 at that time, you get a Brownian bridge, which is a continuous stochastic process on the time interval 0 to t, which starts and ends at 0. Now, you might ask, how can you condition on a 0 probability event, like the process being exactly 0? Well, you might ask that if you are that pedantic. Okay, let's condition on it being very small, less than epsilon in absolute value, and let epsilon tend to 0. In fact, you don't need to condition on anything, just linearly interpolate the Brownian motion between times 0 and t, and subtract off this approximation, and you get a Brownian bridge, independent of the value of b at time t. Anyway, Brownian motion and bridges have a simple scaling property. Scale time by a factor a, and its values by the square root of factor a, and you get another Brownian motion, or Brownian bridge. So you can always scale a Brownian bridge to be on the unit time interval. And I'll just consider these standard Brownian bridges here. A pretty common thing in the study of Brownian motion, not only can you extract the paths of Brownian bridges from the paths of Brownian motion, but you can go in the opposite direction, and you can use Brownian bridges to interpolate Brownian motion between some discrete set of sample times. The probability that the maximum of a bridge is greater than a fixed value x is e to the power of minus 2x squared, also called a Rayleigh distribution. Simple, and this can be proved by a cunning technique called the reflection principle, which I'll explain in a moment. But the absolute maximum, or the maximum of the absolute value of a Brownian bridge, which takes into account the distance it reaches both above and below 0, is a little more complicated. But we can still calculate it, and it actually has the Kolmogorov distribution. So scaling by the square root of 2 over pi, its generalized moments, or Mellin transform, are given by 1 minus 2 to the power of 1 minus s over s minus 1, multiplied by 2 psi of s. And this range, the difference of its maximum and minimum, this has the Kuiper distribution. So scaling by the square root of 2 over pi, again, gives the Mellin transform of 2 times psi. So psi and the Riemann Zeta function appear yet again. not only that, but this is in exactly the same way as with the statistical tests of an empirical distribution that we looked at. I mean, how could this be? Is it just some crazy coincidence? Well, of course it isn't. In fact, if you have lots of samples, n is very large, and you're scaling by the square root of n, then the difference between the empirical and true distribution functions actually converges to a Brownian bridge. At least it does for a uniformly distributed random variable on an interval. And any continuous distribution can be mapped to a uniform one by a continuous change of variable. So you still get a Brownian bridge with the time axis transformed, but that doesn't change the value of its maximum or its range. We can also look at the mean and standard deviation of a sample path of a Brownian bridge. And by this I mean the sample mean and its sample standard deviation. And the sample mean, that's just its integral, or average value, over the unit interval, which is normal with mean zero, not surprising, as Brownian motion and bridges are Gaussian, and you can compute its variance, pretty standard stuff, it comes to 1 over 12. But the standard deviation of the path, that's a little more complex. If you integrate its squared difference with the sample mean, and then you take the square root, it does look rather messy, but it can be worked out, and it's got distribution exactly equal to the Kolmogorov distribution divided by pi. So again, moments are given by the Riemann Zeta function. But why is this? Is this another crazy coincidence? This is saying that the absolute maximum of a Brownian bridge has the same distribution as pi times its pathwise standard deviation. I mean, what? How on earth can this be true? In fact, there's lots of coincidences like this. Take a Brownian motion in 3 dimensions, so its x, y, and z components are independent Brownian motions. And consider the time at which it first hits the unit sphere, sometime t, which is a random time. And half pi times the square root of t, this has the Kolmogorov distribution again. Another massive coincidence. Now, I don't think anyone has a good explanation of this. Something intuitive that would explain it without cranking your way through the maths, computing distributions, and then checking out that they turn out to be the same as just some coincidence. So it's pretty mysterious. And that's why I mentioned in the introduction that no one really understands why the zeta function keeps appearing like this. But not only that, but the proofs of these results don't even involve the same methods. It's completely different maths. For the maximum of a Brownian bridge, you can use the reflection principle to compute its distribution function as an infinite sum, term by term, and I'll explain this in a moment. And it really is quite a fantastic technique, but for the other stuff, the pathwise standard deviation or the time that a 3-dimensional Brownian motion hits a unit sphere, this can be done by moment generating functions, which is completely different. In fact, if x has the Kolmogorov distribution, then twice the square of x over pi has moment generating function equal to the square root of s over sine of the square root of s, which is pretty amazing, right? I won't go further into this here, maybe for a later video, but it's another fascinating characterization of the Kolmogorov distribution. And it's not just Brownian bridges. Other processes can also be constructed by conditioning paths of Brownian motion, like Brownian excursions. There you condition on the Brownian motion hitting 0 at time 1, like with a Brownian bridge, but also that is positive before that time. Or you could just condition on the Brownian bridge being positive. And these processes are important for excursion theory, since all of the deviations from 0 of a Brownian motion are suitably scaled Brownian excursions, so they can be used to break down and reconstruct the Brownian motion. And Brownian meanders condition a Brownian motion on being positive up until time 1, but don't further restrict its value at time 1, it can be any positive value. And in fact, all these processes, bridges, excursions, meanders, they can be extracted from the paths of a Brownian motion in many ways without doing any conditioning. For example, take any fixed positive time t, look at a Brownian motion up until the last time it hits 0 before time t. Then look at the path from this time to time t, and from this time to the next time it hits 0. And this gives you 3 paths, each of which rescale the time axis to go from 0 to 1, and the values by the square root of this scaling factor. So we get 3 processes from one Brownian motion path, and they have distributions of a Brownian bridge, a Brownian excursion, and a Brownian meander. Anyway, the maximum of a Brownian excursion has the Kuiper distribution. Scaling by the square root of 2 over pi, its generalized moments are 2 times psi. The standard deviation of sample paths of excursions has the Kolmogorov distribution divided by pi. And the maximum of a Brownian meander has twice the Kolmogorov distribution. Even more coincidences. Crazy, right? But not so fast. These ones actually can be explained in a more intuitive way. Take a Brownian bridge. Locate the time at which it hits its minimum value. This splits the bridge into 2 parts. First, where it goes from 0 to its minimum, then when it goes from its minimum to 0. And switch these around. And shift up to start from 0. You get a Brownian excursion. And this method of transforming the paths is known as the Vervat transform, and does not affect the range of the process, the maximum minus minimum, nor does it affect the sample pathwise standard deviations, so these are the same for bridges and excursions. Pretty nice. Actually, interestingly, if instead of switching the 2 parts of the Brownian bridge path in the Vervat transform, we instead just flipped the first part in time, and then we slide them up to a line and to start from 0. You get a meander. Pretty interesting, but doesn't actually help us here. But there is a way of translating the path of a Brownian bridge into a meander, and it takes the absolute maximum of the process to twice its value. And that explains why a meander has twice the Kolmogorov distribution for its maximum. This transform is a little obscure. In fact, I could only find one paper by Bien and Yor which describes this, but I couldn't find any link to the paper online. So I've made up my own method, which may be the same thing. So take your Brownian bridge. Let T1 be the first time it hits its absolute maximum. Let S1 be the first time it hits 0 after this. Then let T2 be the first time it hits its absolute maximum after S1, and S2 the first time it hits 0 after this, and so on. And then between each of the times S0 to S1, S1 to S2, and so on, you reflect the process through 0, if necessary, to ensure that it's positive at each of the times Tn. On each interval Sn to Tn plus 1, reflect in both time and space. Reflect the values of your process after each of these times Tns. That's an infinite sequence of reflections. And you get a meander. Not only that, but its maximum occurs at time S1 and is exactly twice the absolute maximum of the bridge at time T1. So the distribution of the meander maximum is twice that of the absolute maximum of the bridge. There's no need to actually work out what these distributions are. Okay, don't worry if that was rather difficult to follow. It's probably easier to actually just work out the distributions exactly. And when this is done, using the reflection principle, which I'll describe, they actually reduce to pretty much the same calculation fairly quickly. Well, the zeta function is all over the place, but does this have anything to do with the Riemann hypothesis? Of course, that's something a lot of people are interested in, so naturally you would ask that question. This hypothesis was conjectured in 1859 by Riemann, says that all non-trivial zeros of the zeta function are on the critical line, the line with the real part equal to a half. And there are zeros at negative even integers, but they're called trivial zeros, and the conjecture does not concern those. In fact, psi does not have any trivial zeros, as they're all cancelled out by the poles of the gamma function. So the Riemann hypothesis is that all zeros of psi lie on the critical line. Now it's known that they're all in the critical strip, and they're symmetric about the real line and the critical lines by the functional equation, but after 166 years no one has proved that they are all on this line. Nor has anyone found any zeros off the line, so it's one of the most notorious open problems in mathematics, and there's a $1 million prize waiting if you can solve it. So if the zeta function keeps coming up with Brownian motion, maybe the hypothesis can be interpreted in terms of Brownian motion. Well, I don't know if there's a good way of doing this. Suppose V has the Kuiper distribution, like the maximum of a Brownian excursion. Then it's equivalent to saying that the expected value of V to the S is non-zero unless the real part of S is a half. But I mean, that's hardly a reformulation, it's not helpful. Maybe something like Lee's criterion could help. This says that the hypothesis is equivalent to all these derivative expressions in terms of psi at s equal 1 are positive. And you could just plug in the expected value of V to the power of S for psi, and you'll get polynomials in log of V. But so what? These are all messy expressions without any alternative interpretation of them. It's not going to help. So no, I don't see any useful way that any of this relates to the Riemann hypothesis. Maybe you can. Let me know in the comments. Or maybe you want to keep it secret and then claim the $1 million prize. The probability distribution of the maximum absolute value of a Brownian bridge is this infinite sum. And the proof of this actually uses a fascinating technique called the reflection principle. Here, you take a Brownian motion and you wait for it to hit some level, and as soon as it does that, you reflect its values about that level. And this reflected process is also a Brownian motion. It's a simple idea, but it's got lots of applications, like in option pricing, pricing barrier options, and so on. Anyway, here, it directly gives an explanation of each individual term in this sum. So let's start with the Brownian bridge. Just a Brownian motion up to time 1 and conditioned on the event that it ends within a small distance epsilon of 0, in the limit of small epsilon. And consider reflecting this process when it hits a positive level x. If the maximum of the process is at least x, then it hits that level and after this time is reflected about level x. And if your original process ends within epsilon of 0, then the reflected process is within epsilon of 2x. But if your original process didn't hit x, then it doesn't get reflected, so now the reflected process is just the original process and is less than x. So writing this out, the probability of the Brownian motion having maximum greater than x, conditioned on ending within epsilon of 0, is the ratio of the probability of the reflected process ending within epsilon of 2x and the original Brownian motion ending within epsilon of 0. But the reflected process is Brownian motion. Its final value is the standard normal distribution, with density proportional to e to the minus half x squared. Send epsilon to 0. We get the probability of a Brownian bridge maximum exceeding x is e to the minus half of 2x squared, or e to the minus 2x squared. This is the Rayleigh distribution. Okay, nice, right? But we want the probability of the maximum absolute value exceeding x, which is the same as the process hitting either x or minus x. So I'll write u for the event that the upper level at x is hit, and L for hitting the level at minus x. So we've just shown that each of these have got probability e to the minus 2x squared. But we need the probability of L or u, which we could approximate as the sum of the probability of L plus the probability of u, but this is double counting the event that both L and u are hit, so I've got to subtract that off. Now, going back to the reflection principle, we can use it to calculate the probability that the Brownian motion hits u then L. All we do is we reflect it twice. First when it hits u, then when it hits L after this. And the second reflection is applied to the already reflected process, which will be at 3x when the first process is at the lower level, and it will be at 4x when the first process returns to 0. So the probability of hitting u then L, conditioned on ending at 0, will be the ratio of the probability densities at 4x and at 0. So e to the minus half of 4x squared. And this works for any number of barrier hits alternating between L and u. Say u then L, then u then L, so on. For n barrier hits in turn, we reflect the process n times, and when the original process ends at 0, this multiple reflected process is at n times 2x, which is just the distance required to go from 0 to u, then to L, then to u, and so on, and return to 0. So the probability is e to the minus 2n squared x squared. and I'll write the sequence of barrier hits by concatenating UL, UL, so on. Going back to our formula for the distribution of the absolute maximum of the bridge, the probability of hitting L and U is the same as probability of hitting L then U, or hitting U then L, which we approximate as the sum of these probabilities of LU and UL, but that double counts the event where both these happen. But if the process hits both levels and both orders, then it must hit U then L then U, or L then U then L. So we have to subtract this off, which again we could approximate by the sum of these probabilities, but now we've double counted the event that hits 4 barriers, which would be LU, LU, or UL, UL, and we can keep on going like this forever. And if we do that, we get this infinite alternating sum. Each term is the sum of probabilities of LU, LU, etc., or UL, UL, etc. And this is exactly e to the minus 2n squared x squared times 2. Done! This is the probability distribution. The reflection principle tells us that the nth term is the sum of the two probabilities for hitting n alternating barriers in turn, starting with U first or with L first, which is the probability of hitting the n barriers in either order, but double counts the event of hitting n plus 1 alternating barriers, hence why we need the following terms. Anyway, we're done with this part. We have the distribution. The only remaining part is to calculate the expected value of x to the power of s. For positive random variables, we'll use a handy little formula here, that the expected value of f of x for some differentiable function f is the integral of the probability of being greater than x multiplied by the derivative of f of x. So for x to the power of s, the derivative is s times x to the s minus 1. We have the integral of the probability times x to the s minus 1, and plugging in our sum for the distribution, we get this infinite sum. And each term is the integral of e to the minus 2n squared x squared x to the s minus 1. And we solve this in the usual way, just change variables. So y equals 2n squared x squared, and substitute this in. It gives us this, s times 2 to the power of minus s over 2 times n to the power of minus s times this integral, which is y to the s over 2 minus 1 times e to the minus y, the gamma function of s over 2. Now this is starting to look like what we want. We have this sum of n to the minus s, but it's got alternating signs. If it was just n to the minus s without the alternating signs, it would be the zeta function. But with the alternating signs is what is called the Dirichlet eta function, which we can compute. We split it up into two sums, first with all the positive signs, and then subtracting off twice the even terms. And if we extract out the common powers of 2 here, we get these two infinite sums, which are both the zeta functions. So collecting them together, we get 1 minus 2 to the 1 minus s times zeta of s. We are done. That completes the proof for the absolute maximum of a Brownian bridge. A similar idea works for the range, maximum minus minimum, and for Brownian excursions and meanders, all using the reflection principle. I kept it symmetric in my description, but the upper and lower barriers can be different distances from 0. It doesn't change much. The probability of hitting them alternately in order is still e to the minus half the distance from 0 to each of the barriers in turn and back to 0 squared, giving the joint distribution of the maximum and minimum of the bridge. And letting the lower barrier go to 0 will give you the calculation for a Brownian excursion, and doing the same thing, but without conditioning on ending near 0, gives a meander. Well, that's it from me for today. I hope you enjoyed this dive into some of the many surprising connections between Brownian motion and the Riemann Zeta function. And these are all covered in this paper by Biane, Pittman and Yor, along with many other examples. I just mentioned a few of them. And I didn't even go into the details of some of the statements, like the sample path, standard deviation of Brownian bridge, or the time for a three-dimensional Brownian motion to hit the unit sphere. Maybe something for a future video. Anyway, that's it from me for today. Please like and subscribe. I'll be back soon, almost surely.